everyone, welcome back to the channel. I'm Julia. I'm the lead developer of GeoChemFoam, and in this video, I'm going to show you how to use it to simulate flow and calculate permeability from a microcity image. For this demo, we're going to use the GeoChemFoam solver simpleDBSFoam. This solver is based on the Darcy, Brinkman, Stokes equation. The nice thing about this approach is that we can penalize the solid phase by giving it a very small permeability. This forces the velocity to go to zero in the solid, which basically behaves like a no-slip boundary condition. We'll go into the detail of the implementation in a separate video. Today, the goal is simply to see how to use it in practice. We start from tutorial 3 from the GeoChemFoam Wiki, Estaillades permeability with microporosity. But instead of a microporous image, we're going to use something simpler, a Bentheimer sandstone CT scan. In this image, voxels with value 0 are porous, voxels with value 255 are solid, and values in between correspond to pore-solid interfaces. What GeoChemFoam needs is, for every voxel, a local porosity epsilon and a local permeability K. We're going to see how the code automatically generates these fields from the CT image. One big advantage of the DBS method is that we don't need a mesh that follows the pore geometry. Instead, we mesh everything, pores and solid, with a simple Cartesian mesh. The pore geometries are then described by the local porosity field epsilon. That makes meshing really easy, especially in parallel. We simply split our domain regularly in each direction. No fancy load balancing, super simple and very robust. Now, OpenFoam doesn't have a routine that creates this mesh directly in parallel. Instead, you would use block mesh to create a local Cartesian grid, then decompose it between processors with the possibility of refining it later, which is not really practical. In GeoChemFoam, we've implemented routines that can directly create this parallel mesh, the local porosity field epsilon, and the local permeability K in a fully scalable way. If you are interested in the details, check out our paper, which is available on arXiv. Right, let's jump into the actual workflow. So here we are in the GeoChemFoam runs directory. I'm going to copy the Estaillades tutorial, which is in tutorial incompressible simpleDBSFoam S subvolume, and call it Bentheimer DBS. And we go in the folder, and what we see is the typical OpenFoam folders plus the script that we have implemented. I'm going to start by opening the createmesh.sh script. And in the createmesh script, you have a lot of user inputs. There are the image name, its dimensions, etc., etc. These currently correspond to the Estaillades image, and we will change them for our image. The image we will use is called Bentheimer 400 5 μm for 5 micron. So this one here, I will comment the Estaillades and uncomment the Bentheimer. So if you're using your own image, you will put the image name here, and here you have to put the directory where the image is located. And this Bentheimer image is shipped with GeoChemFoam and is inside the GCFoam image row folder. So we're going to have a look at this folder. This folder, GeoChemFoam img raw. And in here we have several images, including the Estaillades image and the Bentheimer image. And for each of these images, we have a .text file. This file describes the property of the image. So we're going to use cat to print the property of the Bentheimer image. So here. So we see the size of the image, 400 cube, resolution 5 micron, the type of segmentation, this is a grayscale image with pose 0 and solid 255. We also note that the image is compressed here. So this property we need to add into the createMesh script. So the image format is raw, it is compressed, and the size is 400 cubes, so 400 in each direction. Next is the segmentation type, and Estaillades is a phase-based segmentation, which is typical for image with microporosity. You enter the list of labels and the values of porosity. But Bentheimer is a grayscale image. So we're going to comment the phase option and uncomment the grayscale option. We check pore 0 solid 255, pore 0 solid 255, all good. Next is the minimum epsilon, minimum porosity. And with the DBS equation, EPS cannot be 0, otherwise you'll be divided by 0. So instead, we replace it by a small value. Here, we use E-4. Smaller is better physically, but too small can hurt convergence. So this is a safe option. Next, we define the subdomain. And we could simulate the full image, but here I'll crop it from 50 to 350 in each direction because I want it to be fast. Then we add padding in the flow direction. These extra cells are fully porous and are useful if we want to impose a constant velocity field. Otherwise, we might inject in a solid cell at the inlet. If we are planning to use constant pressure boundary conditions, then we can put the padding to 0 here. But I'll keep it and I'll use 4 cells of padding on each side. So this means the domain in the flow direction is 300 plus 4 for the inlet, plus 4 for the outlet, so 308 cells in the flow direction. Then the resolution is 5 micron, so we enter that. For the number of cells, the most natural choice is 1 cell per voxel, so 300 in each direction. If your machine isn't powerful enough, you can under-resolve the image by putting a smaller number here, but this needs to be a factor of the number of voxels 300. For example, you can put 150. This will mean 2 voxels per cell. You can put 75, 4 voxels per cell, etc., etc. And you will probably want to do this in each direction. I will keep 300 full resolution for now. We won't use mesh refinement here, but we'll come back to it in a future video. I will just put this to false for now. We are running in 3D. The flow direction here is 0, so 0 means X, 1 is Y,
and 2 is Z. And I will choose 2 here. Finally, the parallel decomposition. This machine has 64 cores, so I will use 4 cores in each direction. And now we're ready to run our Create Mesh. Running it is going to take a few seconds. We're creating the mesh, and then we're creating the porosity field epsilon. Here it's done, and we can open it with ParaView. So I will open ParaView. Find my case, it's actually here already, and I load the ParaView loader foam file. So you will get this error here, which means there is no mesh, and this is because our mesh is inside the processor, not inside the constant where ParaView is looking for it now. And to solve this, you close this, and you hear reconstruct case. We will say the case is actually decomposed, and now we'll be looking inside the processor. I'm gonna uncheck the skip 0 time because I want 0. This is where my field epsilon will be. I'm also going to uncheck this create cell to point filter data because we don't need it, and this will be faster then. So apply. We are loading our mesh, and this will appear in a few seconds. It's a relatively big mesh here, 300 in each direction. And here it is. Of course, it's just a big cube. If you look at the surface with edges, we'll see our cells. And we can look at the epsilon field here. And here we see in red are the pores, in blue the solid. And we can see the pad, 4 cells in each direction. Next, we go back to our terminal and we open init case flow. First choice, boundary condition type. We can use a pressure drop or a flow rate. And since we added the padding, we can choose flow rate, which will put a constant velocity field on the inlet. We control this by the flow rate. It's 0 at the moment because the boundary type was pressure drop. We can put a number here, for example, 1 e minus 9 meter cube per second, which is about 3 millimeter per hour. We don't need a pressure drop. We can put it to 0 now. And the fluid kinematic viscosity, so in meter square per second, for water, it's 1 e minus 6. We're using the grayscale model again, so we're going to comment phases, the phases option, and uncomment this option, which is the Kozny-Kármán constant. And so the voxel permeability in the grayscale model will be computed using a Kozny-Kármán type relationship. In the pores, the permeability is effectively infinite, and in the solid, because epsilon is very small, K becomes extremely small. And so the flow is essentially blocked. And this constant here is controlling this. We can leave this 1.8 power 12 for the moment. It is enough to get very low permeability in the solid. Then we will run init case flow. So this creates the velocity U and the pressure P at 0 time. I will clear my terminal to make some space. And next we're going to open the run case flow file. And here the only user input we need to fill up is the total time, which in the case of simple DBSFoam is a maximum number of iterations. We will stop before that if we reach convergence, or stop at 2000 if we haven't reached convergence. And here we're going to leave this at 2000. And we're going to run the run case flow. And it's going to take about 3 to 4 minutes. I'm going to time it. So it's running on 64 processor. And while it's running, I'm going to do some cleanup in ParaView. And we're going to remove the solid phase by using the threshold filter here. So we choose epsilon here, and we're going to remove everything that is between 0.0002 and 1. So this will only keep the cells that are not in the solid. So when we apply it, the solid will disappear. We don't need the epsilon again. And here is our domain, which now only contain the pores cells. We can also remove the padding using the clip filter here in the Z direction, and the actual image starts at 0. So if we want to remove the padding in the inlet, we have to put 0 and -1 here to keep the image. Apply, up, and we create another clip to now clip the other one, which is for this image at 0.0015. And here we don't put -1. So this is going to remove this padding. Here we are, we've removed the padding now from our image. Now we can go back to our simulation, and we see it's run in 3 minutes and 45 seconds. We can look at the simple DBSFoam flow out, which is the log file for our simulation, and go at the bottom, and we can see that we have converged in 202 iterations. And we can look at the pressure field. So if we refresh now, and then we can look at the pressure, for example, here it is. Here's our pressure drop. And we can also use ParaView to plot the streamlines. For this, I'm going to use the stream tracer filter. For this, I'm going to use a point cloud for the seed, and I'll use a bigger sphere. It's maybe -3, and I'm going to use 5,000 points for this. Here are streamlines, and we can look at the velocity inside the streamlines. We can the sphere, and here is our streamlines. Now we can go back to our terminal, and we can run process flow, which is going to process our results and calculate the porosity and permeability of the image. What we get after running this is a poroperm.csv file, and inside we get the porosity, so 0.26, permeability 3e-12 meters square. We have an estimation of the pore size, 4e-5, so 40 micron. Then you have the Reynolds number, the Darcy velocity, and the hydrodynamic tortuosity tau. And this concludes our tutorial, guys.
Thanks for watching. And if you found it useful, smash a like. It really helps the channel. We're going to try to release a video like this about once a month, covering both practical tutorials and more theoretical aspects. If you want to see more GeoChemFoam content, don't forget to subscribe. And if you build something cool with GeoChemFoam, tell us about it. But until then, keep it open, keep it reproducible, and happy modeling with GeoChemFoam.